Equivalence point is when it's what?
Yeah. This is a verbatim definition that we should be relating back to the idea of acid and base. I'll wait for you guys. Go ahead and pull out your calculators and pull out, if you need to, pull out your reading guide for the definition. We need to be active today because you've got some information to practice with. Yeah. No. Oh, sorry. You know what? I didn't assign that reading guide, did I? No. Never mind. Sorry. Thank you, Glenn. Like 5 minutes ago, I said reading guide. You're like, all right.
I was like, wait.
Let me tell you this. Sorry, I didn't assign the reading guide because you guys were taking notes by yourself, so I felt like that was enough. Okay, so the equivalence point. This is a specific case scenario where you actually do something called a titration with an acid and a base. So basically, it's a reaction between acid and base. And what's that type of reaction called? Has it got a specific type of name? Huh? Neutralization reaction. Okay, so it's during a neutralization reaction when the moles of acid equals the moles of base. Equivalence point. It's the point when the acid moles equal the base moles. That's not too complicated, right? There's something else with this, though. We're going to have to actually talk about the pH when they neutralize each other. Is the pH 7? What do you guys think? Maybe, right? The answer is maybe. When would the pH be 7? Right, so specifically the one we're going to focus on, if it's strong acid, strong base, they neutralize each other to make a pH of 7. But what about having an acid and base reaction, but it's a strong acid and a weak base? It's going to be more acidic. So neutralization does not mean neutral. Neutralization is a process of acting of a base and an acid neutralizing each other, but it does not always mean it's going to be a pH of 7. If it was a strong base and a weak acid, what would the ending pH be?
More basic.
More basic. So it depends on what's happening. Okay, so this is what's happening inside. Please not get up and throw away trash in my class. It's distracting. Whenever you have this is happening on a molecular scale, you can't see that very well because they're so minuscule, they're very tiny. But what we can see is an indicator changing colors. We know one indicator in particular that changes from colorless to pink is, say it again? Phenolphthalein, right. So phenolphthalein changes color. And so when it changes color, we automatically know it's gone from kind of a 7-ish pH to maybe 8, 9-ish pH. So the end point is a place that happens also during the reaction, but it has a color change that's associated with it, and so we can actually see it. And that's when we actually tell ourselves to stop the titration, in the titration. So it's when the indicator changes color during the titration. And the titration is this same scenario, the acid-base reaction. So the titration is kind of like the lab procedure, but the lab procedure involves us adding an acid and base together. We cannot see the equivalence point, but we know it's there. We can see the end point because we can see the color change. But a really good titration will have these 2 points very close to each other. They may not be exactly the same point, but they're very close. Okay, review. What is molarity? Whatever what? So moles of solute, or in this case, our solute is going to be either an acid or a base. So solute is just acid or base for us, over liters of solution. Okay, so thinking back to how King Henry died by drinking chocolate milk, blah, 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 with the number scale, what units would occur if I divided the liters by 1,000? Right, so liters would go to milliliters when I divide by 1,000. What would happen to moles? What did I add? What prefix did I add here? Milliliters. So these are millimoles. Great. There is such thing as millimoles. It's just basically like I could go kilomoles, picomoles, nanomoles, gigantomoles, whatever. I can add a prefix to it. It's just sometimes we have a situation where we use a very small amount. Maybe we use 2 milliliters of a substance. How many liters is that? 2 milliliters. How many liters? 0.002. And that number sometimes is hard to conceptualize, so we just say 2 milliliters or 2 millimoles because it's an easier number to work with. So sometimes we'll use this, but it won't be at first. I'm going to get you started on normal stuff, and then we'll go to millis. Okay, so this is what a titration curve looks like. Okay, sketch this. And I'm going to sketch another one in a second. I'll leave it like that so you can see most of the numbers. You do not have to like put this to scale by any means. Give yourself a simple sketch, and we're going to talk about what the values mean and where they are probably most important. Who's seen one of these graphs like this before? Maybe in your book. You looked in your book, but it's probably the first time you've seen this. Okay, so looking at the graph, you can tell me what's happening here. Well, I'm going to start down here. So tell me what this lab setup might look like. Obviously, I have what kind of equipment? A flask, and I've got some stuff in it. That stuff in there, is it acidic or basic initially? How do you know it's acidic? We're below 7 here, right? So this right here is my initial reactant. And you know it's an acid because its pH is like 1 right there. And this is, you can see, at 0 before any base has been added. And what base is this? Sodium hydroxide, right? Okay, so before any base is added. So what happens as you add base? What happens to the pH? It slowly goes up, right? Slowly goes up, slowly goes up. And so right here, you've got a lot more acid than base still, right? So there's more acid than base, and that's why the pH is still below 7. Then all of a sudden, we add just a drop more of base. So we're at like, let's say, 39 or so. I drop another milliliter of base, and I'm at 40, and it goes whoop, way up high, right? It's a very quick incline of pH. That's because of the log nature of how pH is related to the concentration. The log is that exponential growth there. Can you kind of see that as exponential growth? That's exactly what you should be seeing. So at this point, though, that's when I have 40 milliliters of base added. I have whatever initial volume of my acid I originally had, and I can tell you definitively that this is an acid-base titration between a strong acid and a strong base. Why? Because right smack dab in the middle of this vertical section is called the equivalence point. And the equivalence point shows me that when moles of acid equal moles of base, the pH of that situation is 7, which indicates to me that had to have been a strong acid and a strong base. So you can see here, it's definitely a strong base. That's not a question. What acid could this be? You got a couple to choose from. Let's go hydroiodic acid. So this could have been high, this could have been HCl, this could have been hydrobromic acid, this could have been nitric acid, this could have been any of those 6 strong acids, and that's how we know that it's strong acid because it's pH 7. Okay, so in a titration, when I have a flask, I'm adding slowly base to it. I'm going to maybe, depending on what indicator I have in the flask, I might see a color change here, and so if I use methyl red, I'll see a color change early. If I use phenolphthalein, I'll see a color change later, past the equivalence point, right? Either before the equivalence point or after the equivalence point. What is that thing called? What's that point called when the color changes? The end point. So if I were using phenolphthalein, the end point would be right there. Is the end point equal to the equivalence point? No. It would be great if it was, if they overlapped a little bit more, but it's, we got indicators to choose from. Not every single time is it going to land right on it. So the end point actually in this case is higher than the equivalence point, but that's okay. At this point in the lab, I would tell you to stop. Do not add any more. If you add one more drop of base, that's called overshooting, right? Because you're going to be overshooting the end point. And so because we don't really use pH probes during the whole titration, we use indicators, we have to really, really closely watch the color change. And so if we overshoot, though, you'll see the pH will eventually start to kind of get a bit more basic, and then it will level out at about pH 12. And so that's the end of it. So what we want to do in the lab is whenever we add base to acid like this, we're going to watch for a color change, and when we get to the color change, we stop the titration, and then we calculate from there. So the real purpose of this is, first of all, maybe it's determining what the acid is, and maybe it's actually determining what's the molarity of that acid. Because you can tell from the information given, let's see here, Oh, and actually, normally I wouldn't give this to you. We took 40 milliliters of hydrochloric acid, but in our lab, which we'll do tomorrow, and one of the simulations you'll do today, this would be unknown. So I wouldn't give you the concentration of hydrochloric acid. You would do some data collection through this titration, and then you would figure out what the unknown concentration is. But we would be constructing graphs like this. Okay, so this one's pretty symmetrical. Let's think of a situation. Yeah.
Like, what's it? Is there 2 endpoints? There's 2 colors?
Well, I was just showing, I have 2 different indicators on here. We would only use one, but it's showing you that endpoint. Depending on which indicator you choose, it could be before or it could be after. Good point. Okay, so let's look at different graphs with different scenarios. So this was strong, strong. Hold on. Okay, this one, the strong one, looks like we had earlier, right? The weak acid is going to actually start up at a higher pH. Why does that make sense? You might want to sketch some of these as we go, okay? Why does it make sense? Right, the stronger the acid, the lower the pH, because the more H plus is in solution. So weak acids just have a starting point that's a little higher. So they have a higher pH. And I don't know if you can tell, there's like a little tail, little wiggle in the beginning of it. That sometimes will indicate to you that it's weak. But really, if you're looking at the pH, it's pretty obvious between the blue and the red graph here that the weak one is the blue graph. What else do you notice, though, as you kind of keep going through the titration? What happens eventually? Yeah, they eventually even out. Oh, and I didn't write this on the other graph. But at this point, before the equivalence point, the acid is greater than the base. The amount of acid is greater than the amount of base. If you're adding the same base to both of these acids, eventually they're going to even out because the base rules. So the base is greater than the acid, meaning the base is in excess and the limiting region is the acid. And so that's why the base controls the pH from there on out, and that's why the graphs overlay each other from there on out. Okay, so if you sketch this, you'll be able to answer this probably easily. And I'm going to go in the color scheme given. How do you figure out the equivalence point when you look at a graph like this? Basically, you look at the vertical section, so from like here to here, and then you eyeball it about halfway. So if I go about halfway, where's the pH of the red graph? Right, so that one's about 7 right here. So, and that one is going to be the strong acid and then a strong base. I'll just add sodium hydroxide here for clarification. It's a strong base as well. That's why that one's 7. But look at the blue graph. If you go to the vertical section of the blue graph, you're going from about here to here. Where's that pH? That equivalence point? Maybe like 9, maybe 8.5, 9. Yeah? So I'm just going to call it pH 9 just so you can tell it's above. So why does it make sense between a weak acid and a strong base that the pH, the equivalence point is 9? It's closer to the basic region. When you're a weak acid plus a strong base, that's going to yield a basic solution at the equivalence point, and that's what pH 9 is. It's a basic solution. So you see there's a difference. Graphically, and when you know that you add your pHs together, they're different. Look at this one. So in every example I have used so far, we started with acid and we added base. And what happened to the pH? It goes slowly up, right? What am I doing here? And slowly adding acid, right? So in the pink graph here, my pH starts off at 11 or so, right? That sounds like it's pretty basic. It's kind of actually not still as basic as it could be. 12, 13, those are pretty strong bases. But you can see that I have my base, I'm slowly adding acid, boom, there's the vertical section. So I'm going to do this one in green. So here's my vertical section, and here's my vertical section. What's the equivalence point pH? 5-ish. Yeah, about pH 5. Okay, pH 5. So knowing that, without even looking at the axes or who's being added to what, would that be between a strong acid and a strong base, weak acid, strong base? What would the combination be? Weak acid and, no, not weak acid. I like to listen to you, but that's not correct. Say it again. Strong acid and, say again, weak base. Weak base and strong acid means the strong acid pulls the equivalence point down closer to the acidic region. That's why it's pH 5 and not pH 7. Thumbs up if you get that. how the combinations work. Oh, okay, let's do one more. Where's the equal most point on this blue graph?
3.
It's like 3. It's actually a really short vertical region, and actually where that green line is about the equivalence point. So that green line is about pH of 3. So that must be like strong acid and like weak base, super weak base, depending on what's added. And that is actually the bicarbonate ion, and it's a weak base. Okay, give me a thumbs up if you're done sketching. Yeah.
I don't understand how much is from 2 different pHs, like what does that mean?
You mean on the 2 different graphs here? So there are 2 different titrations, but they're overlaid each on the same graph just so we can compare them. It's not the same titration. They're 2 different experiments. I just have them on the same plot so you can see the difference. Good question. Sorry about that. Yeah, 2 different experiments. Okay. This one, I have 3 different titrations I've run. And this is going to relate back to how do we know if something's a strong acid or a weak acid or a strong acid or a weak or a base based on the K value. You guys remember the Ka value from one of the set of notes is on weak acids and weak bases? Do you need to count for our flannel? Turn my light on over there. Stand up if you are participating in Spirit Week. It's pretty obvious if you are, but stand up for me. Yeah, get your plaid on.
What's the amount?
14 out of 20.
Oh.
Thank you. Okay, so in this one, I'm going to give you a brief reminder on what does Ka mean. Ka tells about amount of acid dissociation. And dissociation just means to break apart. Like if I don't want to be Matt's friend anymore, I'm going to disassociate with him. Okay, so there would be like a separation. So looking at the differences between these acids that are the starting acids, right? The starting acids are, you can see them on the very left side. Which would be the weakest acid? Red, blue, or purple? Or red, blue, or pink? Definitely red, right? How do you know? Right. You're basically saying this is the weakest acid. And that actually tells us that has the smallest Ka value. Ka is coming up in 2 days for us. That's equilibrium. But it does relate to acid base sum. So obviously pink down here would have the biggest Ka value, meaning it's the strongest acid. Thumbs up if you got your relationship there. Okay. Do me a favor and pull out your notes. Oh, I'll go over the diacritic stuff later. Pull out your notes for titrations. They're on your, yes, I think I printed questions. You'll need your calculator and you might need your periodic table. Let me have their notes handy and I'll see if I have the printed for you. As long as you get some throwaway trash in that slot. I actually did not copy those, so you're going to write down what you need to. I recommend writing down what a titration is first. I'll be quiet and let you guys write down some stuff, because you're going to want some guidelines on how to solve problems. But what I just read at the top for a titration, it requires us to use some fancy equipment that helps us determine volumes, and then we analyze those volumes. So to say that simply, we just call that volumetric analysis. And we do this volumetric analysis of an unknown concentration to determine that unknown concentration. And that's what that blue information up there is indicating to you. And I'll tell you what the standard and unknown thing is in a second. I'll actually pass. Volumetric analysis. So this flow map thing probably makes minimal sense right now, but I'm going to try to explain it to you before we start a question. Whenever you have a titration, you always have one reactant of known concentration and one reactant of unknown concentration. So that one that's of known concentration, we call that the standard. So it's another way to say I have known concentration. We call it the standard. And so you'll see that reference throughout. Sometimes we call the one that's of unknown concentration, we call it the analyte, because we're analyzing that one to figure out its concentration. So there's just two couple ways to say it. You can either call it known or standard, or you can call it unknown and analyte. And a lot of times whenever we know the concentration of the standard, we eventually come to the point where we actually find the volume that we use of the standard to neutralize this unknown. So that actually means we know two things about the known. We know it's both its molarity and its volume. And if I know the molarity and the volume, what else can I find out from those two values? The moles. Do you guys remember M times V gives you moles? M times V gives you moles is going to be your best friend for the first part of every single one of these problems. And that's what I've indicated here. Volume of standard can get you to moles of standard. So what are you going to do with that volume? You're going to multiply it by the molarity. And that's how you get to moles of the standard. Well, then you can see I'm going from moles of standard to moles of unknown. Well, how have we always gone from moles of something to moles of something else? Mole ratio. So what do you think I probably have written before I even started the problem? A BCE. And then once I get to moles of unknown, I might stop there. I might take my moles to grams, depending on what the question is asking for. And then if it doesn't ask for grams, it might actually ask me for the concentration of that unknown. And then if I know I have moles, I'm probably going to have volume given to me someplace in the problem. And that's why I say divide by volume of the unknown to then solve for molarity of that unknown. So either we're going to be getting from moles and going to grams, or we're going to be going from moles to molarity based off the data given in the problem. So we're going to go through a couple different examples of that. Before we go into that, though, this is what you would use for a titration. This is called a burette. The burette has two pieces to it. I don't know if you can see that. Do you see the tiny graduations there? Okay, it actually goes from 0 to 50. You never can go past 50 because there's no graduations down here, so that's inaccurate. You don't know the values. So if you have this filled up to the 0, you would call that 0. You do not call it 50. You call it 0. You read exactly what it says here. And let's say I'm titrating into this flask, and this would be held up like by a clamp at your stations. This little guy down here is called the stopcock. Okay, it moves when it's parallel. This is going to allow the titrant to flow through. When it's perpendicular, it stops it. Okay, so in here, all you do is just let it out a little bit, and then you turn it and close it. Let it out a little bit, turn it and close it. Or you can go really fast, and do one big flip, and it actually lets out about a half a milliliter at a time. So let's say I titrate down to the 24 mark. That means I literally dispensed 24 milliliters of my known into my unknown. And then let's say at that point in time, it changed to pink. It changed colors. That's when I would stop. And so then at that point, I would have 24 milliliters of 0.1 molar sodium hydroxide or something like that that was titrated into 50 milliliters of acid. So I know the volume of the acid, I know the volume of the base, I know the molarity of the base, but I don't know the molarity of the acid. And that's where I get the problem. That's where we're going to start right now. So let's go ahead and write down our knowns, and then we'll go through this problem together. So student, this could be you, titrates 20 milliliters of a sample of, another marker, a sample of hydrobromic acid. The titration requires 20.05 milliliters of 0.1819 molar sodium hydroxide solution. What is the molarity of the HBr? So we just read a lot. Let's kind of write down our BCE first, and then let's write down our knowns. So what is reacting? Okay, so HBr plus sodium hydroxide. This is definitely a neutralization reaction. but simply just a double replacement. We're going back to our old types of reactions. So doubly replace, and I'll put a plus minus up here just so we can make sure we know who's going to be free pairing. Go ahead and tell me what the products are. HOH and NABR. And these were all one plus and one minus charges, so there are no subscripts, or no blatant subscripts. They're all ones. Okay, so let's go ahead and figure out, based off the reading, which is the unknown. Which reactant? HBr, because it says find what is the molarity of HBr. So that's our question. So I'm just going to put unknown here so we remember that's who we're looking for. So then what is sodium hydroxide? The known. The known is sometimes called the titrant too because it's in the burette. So that's another word I said earlier. Burette is the equipment that you would be using to do the titration. Okay, so what do we know about the known? What two things do we know? Okay, so what is the molarity? 0.1819, and I'm just writing it underneath so I can keep my information organized. What's the amount of titrant used? 20.05. So check, I've used both of these. What else do I know? Of the base, of the acid, right? So I know that there's 20 milliliters here that I've used. Sorry, my stuff's all behind now. But I don't know the molarity. My question is, what is the molarity of that acid? So if you set it up like this, it'll help you organize your information a bit. Now here we go. We're going to start just like I stated previously above, how to start any types of problems. What does it say on how to start? Volume of standard times the molarity of the standard to get the moles of the known. Okay, so I'm literally taking these values here and I'm multiplying them together. But if I'm using molarity, I need to put this into what value first, or what unit? Liters. So I'm going to go ahead and put that in liters. So 0.02005 liters times the molarity of the base. And so I'm actually going to break that up into its actual units. So 0.1819 moles of sodium hydroxide over liter of solution. So far, what cancels? Liters of solution. Okay. Now we're in moles of sodium hydroxide. What's the next step on your little cheat sheet? How do I get to moles of the unknown, which is hydrobromic acid in this case? Mole ratio. What is the mole ratio here? 1 to 1 because everything is balanced out as ones. So I literally you have to show me this step. Even though it's 1, show it to me because it shows the concept of what you're doing. So 1 mole of sodium hydroxide based off the 1 up here, and 1 mole of HBr based off the 1 up there. So now what cancels? This has been a while for student chemistry. Moles of sodium hydroxide, but the number, of course, is still there. Now we're in moles of hydrobromic acid. What is our question again? Solve for the molarity. And if you're like, oh, I can't remember what molarity is, write it out for yourself. You know it's moles over liters of solution. But it's actually the liters of acid in this case. So, I'll show you both ways. Tell me what this is right now. Calculator. Everybody have a calculator out so you can practice. What is that so far?
0.003647.
Can you get that to me in scientific notation? Huh? There's a bucket. I don't know where the bucket. Oh, the bucket's right over there. Anybody needs calculators? There's a bucket in the corner. Lizzie, take this for now. All right. What's the number? 3.65 times 10 to the negative third? Okay, that's our moles of acid, right? Now I need to take this number and divide by the liters of acid. How many liters of acid did I use? 0.02, because it's 20 milliliters, so that's bouncing the decimal back. That's 0.0200 liters. Okay, so moles over liters is going to give us molarity. And then what is that molarity? How people calculated? My calculator's down here. The more, thank you. 0.1 what? 23 molar. Okay, I'm going to keep it there for a second. Okay, and that's because we actually have 4 sig figs throughout, so I'm keeping the 4 sig figs. That should have had one more number, but that's okay. So, does this make sense? And I want you to think about it in a 1-to-1 mole ratio. If I had 20 milliliters, about 20 milliliters of sodium hydroxide, which is 0.1819, and it neutralized 20 milliliters of HBr, shouldn't I need about the same amount of both at the end? They're going to be approximately the same molarity? Because they're almost, if it's like 20 milliliters and 20 milliliters and they cancel each other out, then they're probably about the same concentration too. Well, that's pretty dang close, so I feel good about that answer. Yeah.
Why don't we just use
M1V1 equals M2V2 is now, it's only true if that's only good for 1-to-1 ratios, which this one is, but the AP exam College Board told us to stop using that in AP Chem and Honors Chem. Because if you go to Honors, then you'll have misconceptions. They told us to stop using that. That's why.
I could have made that problem so simple.
Well, it's because conceptually people don't understand why M1V1 works. So it's just perpetuating misconceptions. So I'm trusting in them and doing what they told me to. So, okay, so vinegar, this is one like our lab for tomorrow, okay? Vinegar can be acid. Okay, vinegar can be tested is what that means. Is vinegar an acid or base? An acid. It's got acetic acid in it, okay? So vinegar can be acid, determines acetic acid content. Determine the molarity of the acetic acid in a 15 ml sample of vinegar that requires 22.7 mils of 0.55 molar sodium hydroxide to reach the equivalence point. Whew, seems like a huge problem, right? What's your first step? Okay, ready when you are. Vinegar has a compound to it that we're interested in, which is what? What's in the front? HC2H3O2. Okay, that's acetic acid plus. Yields. And I'll put a parentheses around my acetate so you keep it together and don't be a homewrecker. Makes what? Shout it out. I want you guys to. Thank you, because we're getting a little behind here. Keep going.
Plus,
Okay, you'll see again, this one is a 1-to-1 mole ratio. So I'm starting this off easy because you'll see there's no subscripts that need to be accounted for. What's the information for acetic acid that we know? 15 milliliters, and that's it, right? Do we know the molarity? No. Okay, what else do we know? 22.70 milliliters of sodium hydroxide and 0.550 molar. Okay, and I'm going to show you how to do this with millimoles this time. And if you get it, you will use it, you will love it, you won't have to change any decimals. Where's the marker? But if not, you're going to stick back with your liter forms. So whenever you use millimoles, you're going to take the standard again, but I'm not going to change this to liters. I'm going to show you how I implement millimoles at first. So I'm going to take my 22.7 milliliters of my base solution and multiply by what? It's what? I am not changing it to liters. So I'm actually going to stick with this. Nope, I'm taking basically again, I'm taking M times V to give me moles, but this time it's called millimoles. So I'm taking my milliliters and I'm going to multiply by 0.550, watch now, millimoles of base over 1 milliliter of the solution. So if I wrote millimoles over milliliters, is that not the same as writing moles over liters? The number is exactly the same. You'll notice I didn't change the molarity whatsoever. So if I take away that M, and take away that M, it's moles over liters. And that's why I'm allowed to do that, because it's the same ratio. It's just downscaled a whole, like by 1,000. So milliliters and milliliters cancel. Okay, so then what's next? Yeah, what's that mole ratio? 1 to 1. So this is 1 millimole of acetic acid over 1 millimole of base, sodium hydroxide. And so it's just the same thing. I'm just showing you a different variety of units here. Millimoles of sodium hydroxide cancel with millimoles of acetic acid. Millimoles and millimoles of sodium hydroxide. Now, earlier, what did we do right here? And then we got moles, though, right? So if I stopped here, what unit would I achieve? Say again? Millimoles, right? And then what would I divide by? I want to get some molarity, remember? I would just divide by milliliters. The milliliters given to me right here. But instead of stopping, calculating, and then dividing, can't I just multiply by the reciprocal? Yeah? Can't I just go like times 1 over 15 milliliters? So this is just a shortened way to keep your work in one big step versus choppy steps. It doesn't matter to me. I'm a one-stepper, so oops, I didn't mean to cancel that out. That does not cancel. I like to do it all at once, but if you need to chop it up, that's totally fine. I just want you to notice that millimoles per milliliter are what's left, and if I have millimoles over milliliters, I can actually cancel the milli part, so that little m gets canceled and little m here gets canceled, so what units are left? Moles over liters, and isn't that just molarity? There you go. That's how you use millimoles. So now in your calculator, take 22.7 times 0.550 divided by 15. Here's that other marker. What is it? 0.832 molar of the acetic acid. And then your job is to reflect on this. If we used almost 23 milliliters of the base, and only 15 milliliters of the acid, and they're in a 1-to-1 mole ratio, who's more concentrated to neutralize each other? It requires less acid to neutralize all that base, right? So who should be more concentrated? The acid should be, because it requires less of it to neutralize all the moles of base, and that makes sense. That's 0.83, while that one's only 0.55. Okay, one more for the road here. And actually, I'm gonna do one. Oh, no, this is what I need to do. Okay, this involves pH. Here's our new solution, or our new question. You guys read it right after BCE first. All right, what's our BCE, guys?
SR
So strontium hydroxide parentheses 2, right?
plus HCl gives HOH.
Good. So strontium chloride, SrCl2. Where do you need balance? Okay, so now we've got one that's not a 1-to-1. Okay, that's why I wanted to do this one. You guys write down your values. What values are relevant here for sodium hydroxide or strontium hydroxide? HOH, thank you. I was like, I knew there was an HOH over there. So what values are relevant for strontium hydroxide? Anything?
20 milliliters.
Thank you. And then hydrochloric acid, you've got 43.03 milliliters of 0.1159 molar. So the first question is what's the molarity, right? So that's our very first question. And then the second question is what's the pH of the resulting solution. So we'll get to that shortly. All right, so what are you starting with? Are we going millimoles or are we going normal moles? Millimoles? So I'm cool with that. All right, what am I starting with?
43.
Good, you're starting through known, so 43.03 milliliters of HCl times, right, so I don't change the number, it's 0.1159, but what goes here? Right, millimoles of HCl over what? 1 milliliter of solution. So far, what cancels? Milliliters. Okay, next.
Times mole ratio.
So what's going on top?
2 HCl.
Lies.
No,
Top.
1 HCl.
So 2 millimoles of HCl on bottom. And what goes on top?
1 SR.
So 1 millimole of strontium hydroxide on top. Okay, so then is it okay if I go ahead and do the division by the volume instead of stopping at millimoles and then dividing by volume? I'm just going to do it in one swoop. So 1 over, so multiply my reciprocal, 20 milliliters of the strontium hydroxide solution on bottom. So millimoles of HCl cancel, and so the only units left are millimoles of strontium hydroxide over milliliters of strontium hydroxide solution. So millis cancel, leaving us with moles over liters. So you guys tell me what you get when you get there. 0.1246 molar. Is that what you said? Everybody agree? Okay. So I do need 4 sig figs. So as long as that doesn't need to be rounded, we're good here. 4.7. Okay. I thought I heard a 7. I couldn't remember. I put my answer key in front of me. Okay. Question 1 done, guys. Now, cut off on the pH of that solution. You're like, gosh, that was so last week. I'll wait on you. Tell me what you can figure out from this original concentration.
Concentration of OH.
Okay, I can immediately find, I know it's a base because it's hydroxide, right? And then I can immediately find the concentration of OH. How? What is it? Concentration of OH. No. Multiply by 2, thank you. So this is concentration, right, of the base. Well, this base is special. This base, when it dissolves in solution, hold on, is it a strong base? Is it part of the B?
Yes.
Yeah, it totally is. Okay, just making sure this is 100% ionization, right? So that makes, what 2 ions does it make? SR 2 plus and
OH minus.
how many of them?
2 OH.
2 OH minuses. Okay, so this is the star here, okay? This 2 means I make 2 hydroxides. So whatever my concentration of this is, that's of the base, strontium hydroxide. But when it dissolves, it makes double the hydroxide. So this number needs to be doubled to give me the concentration of hydroxide. So like 0.2494. Thank you. Okay, so now, knowing our hydroxide concentration, what can you now find? And you can go 2 ways with this. Tell me what you know. You can do what? Let's go find the POH first, okay? So this is what some of you guys want to tell me earlier. What's the POH equation? Negative log of OH. Good. So when you plug that in, negative log of 0.2494, what do you get as your POH? Calculator.
0.6031.
Say again?
0.6031.
0.6031. Okay, so that's POH. POH is harder to rationalize because you don't know the POH scale, you know the pH scale. So how do you get pH from POH? There you go. You know, again, pH plus POH is 14. So then you subtract, so pH is 14 minus 0.6031. So what is that? 13 point what? Is it 0.6 or just 6? 0.6. So that's 13.3. Thank you. I can do math, but just not right now. Okay. So then this is the pH, right? And then you reflect. Does this make sense for the pH of a strong base? Heck yeah, it's almost 14. And it's fairly concentrated. Oops. Yeah, that's fairly concentrated for a base. So yeah, approximately 14, we're feeling good about life. So do you see that I can combine pH calculations with titrations a wee bit? Yes. Okay, so it is almost 11. Let's do this in rows and I'll tell you what's going on. You ladies here, go grab your Chromebook. As soon as they start sitting down, you guys, and then so forth, okay? Take a break for another minute and grab a Chromebook. Just wait for them to kind of cycle through.
Yeah.
Oh, and yeah, while you guys are grabbing things, I told you about the test. We're going to wait. We'll do the test before. It's like the 17th or 18th. But 19B, you should be 100% comfortable with now because those last 3 questions, 7, 8, and 9, or 6, 7, 8, go ahead, guys. You should be able to do with your titration work now, okay? So you're going to do a titration web quest for the last 30 minutes or so. I do have 3 more questions for us to practice, and I might let you guys practice those tomorrow. Let me see how far the web quest goes today before I make my final call. All right, you guys go ahead and get up. Go to my website as soon as you can. Go ahead, guys. This last row. They'll move out of your way. So scroll down to Unit 7, Documents. You guys on there? Is it slowly coming up? Okay. And I'll let you guys spread out in a second. I just want to show you how to go from here. You will need paper to write some of this math and stuff like that down on. Yeah. I'll try again. If not, there's you can log onto another computer if your Chromebook is having issues. Okay, so give me your eyes for about 30 seconds here. Eyes, make sure you just get logged on so that it will start pulling up. But when you go to my website under Unit 7, towards the bottom it says Acid-Base Chemistry Web Quest. There's a PDF and a Word document. It doesn't matter which one you choose. They are the same. And when you first pull it up, it says Titration Definition, Acid and Base. That right there you can do from your brain. You don't have to click on the links, but you can if you want to. The virtual titration brings you up, and it will talk to you. So if you have earphones, you can put them in. If you don't have earphones, just like turn it on quietly so that you can hear it, the guy talking to you. So let's see if he talks. He's also singing music. Okay, so he goes through it. So if you miss a step, you cannot reverse. So if you want to sit with somebody and maybe kind of go baby steps with them, so if you miss something, you're like, hey, hold on, let me see that real fast. That might be beneficial. If not, you have to start over and click through it. Okay, so you are going to have to sketch some things. This is what the titration setup looks like. If you have questions, let me know. Spread out, get a piece of paper out. You should be able to get this done by the end of class. We shall see. Yeah. Yeah, that's totally fine. So if your Chromebook's not wanting to connect, then find somebody who loves you and will let you sit next to them, and just kind of keep on.